Hello there, and welcome to the Sleepless Scientist, a quiet corner of the universe where your thoughts can loosen and wonder drift softly into rest. Tonight, our journey will follow one of the most elusive mysteries in all of physics, the speed of light, what it means to reach it, why nothing can surpass it, and what might happen if something ever did, because at that point, you wouldn't just be moving through space, you'd be stepping into the flow of time itself. But before we begin, I'd love for you to take a moment to like this video and subscribe, only if these calm explorations truly bring you a sense of peace. And when you're ready, share in the comments where you're listening from and what time it is for you right now. It's always a quiet joy to see this constellation of listeners scattered across the world, each glowing in their own little corner of time. Now, settle in. Dim the lights. Let the soft hum of your room or the rhythm of your breathing be your background music. And if your mind begins to wander, let it. That's part of the journey too. We'll still be right here, gently unfolding the story of light, time, and everything that moves between them. Imagine a room in complete darkness, a darkness so total it's almost a presence, thick, quiet, untouched. Now picture the tiniest flicker, a spark from a match, or the thin beam from a distant flashlight. That sudden, quiet arrival of light changes everything. The room is no longer just empty, it's defined. Shapes take form, shadows stretch, colour appears from what seemed like void. But what is light, really? It's not a simple question. For centuries, philosophers and scientists debated whether light was a stream of particles or a ripple in some invisible sea. In truth, it turned out to be both. A strange, beautiful contradiction that somehow still fits together. Light travels as a wave. It interferes, bends and diffracts like ripples on a pond. But when it lands, on your skin, on your eye, on a telescope mirror, it arrives as a packet, a photon, a tiny burst of energy that acts like a single, indivisible thing, and light doesn't carry mass, not the way you or I do. It has no rest, no pause, no weight. It is always in motion. In fact, it can't ever stand still. There's no such thing as a photon at rest. It would be like trying to imagine a river with a frozen current. It's not just unusual, it's impossible. That's the first hint that light doesn't live in our world the same way we do. It travels at nearly 300,000 kilometers per second in the vacuum of space. That's about 7.5 times around the Earth in just 1 second. But even that immense number doesn't quite capture the strangeness of what's happening. Because the speed of light isn't just fast, it's something else entirely. It's a limit, a cosmic boundary, like the speed limit written not on a road sign, but into the very geometry of reality. And here's where it begins to feel almost dreamlike, because no matter how fast you move, or where you're standing, or which direction the light is travelling, you will always measure it going exactly the same speed. Not faster, not slower, just the same. If you were drifting slowly through space and turned on a flashlight, you'd measure the beam racing ahead at 300,000 kilometers per second. If you were on a train or a spaceship or clinging to the back of a comet, same thing. Even if you were somehow flying toward the light, it would still approach you at exactly that speed. It's not you adjusting to light, it's the universe adjusting to keep that number constant. That constancy is what makes light more than just illumination. It becomes a reference point, a cosmic heartbeat. Everything else bends around it. Time, distance, even simultaneity. That quiet belief we hold that now is something we all share. It begins to crumble when faced with the speed of a light. But for now, just stay with the light itself. Close your eyes unless you're driving. Picture a beam of light leaving the surface of the sun. It takes about 8 minutes to reach us here on Earth. But for the photon, if we dare to imagine what that would feel like, For the light itself, those 8 minutes don't exist, because time does not tick forward for light. From the moment it begins its journey to the instant it strikes your face, no time has passed, not even a sliver. That's the curious paradox. From our view, light travels, it moves, it stretches across space. But in the frame of light, if we can call it a frame at all, it doesn't experience motion, no duration, no passage. It is born and arrives in the same breath. The journey and the destination are one. It's a little like memory, how a scent or a song can carry you instantly to another place, another version of yourself without any time in between, a kind of inner speed of light, connecting moments that feel distant, yet arrive together. And here's something else. Light has no colour, not until it touches something. The colour you see from a beam of sunlight, scattered in a raindrop into a rainbow, is not a property of the light itself, but how it interacts with your eyes, your mind. In the vast vacuum of space, photons travel without hue, silent, invisible, waiting for a canvas. That means every painting, every sunrise, every glimmer of ocean is the result of light slowing down, being absorbed, re-emitted, bent, and interpreted. Light in that way is not what we see. It is the medium by which seeing happens. It is how the universe speaks to us, quietly, constantly, always moving forward even if it never feels a single second of the trip. So when we speak of the speed of light, we are speaking of something that does more than race across space. It defines the rhythm of causality. It tells the universe what came before and what follows. It sets the stage on which the story unfolds. And yet, for light itself, there is no stage, no sequence, no awareness, only motion, only now, only that single, perfect heartbeat of existence, flickering endlessly through the dark. Let's linger with light a little longer, this companion that touches everything yet leaves nothing of itself behind. We so often think of it as obvious, everyday, even mundane. Flip a switch, and there it is. Step outside at noon, and it's everywhere. But the closer you look, the stranger it becomes. The more familiar it feels, the more it seems to slip between your fingers. Light doesn't behave like anything else in the universe. It doesn't speed up or slow down depending on who's watching. It doesn't age. It doesn't rest. And perhaps most unsettling of all, it doesn't truly belong to time the way we do. Imagine you could somehow transform into a photon, not in some sci-fi way with flashing lights and a dramatic musical sting, but in a thought experiment, a gentle unfolding of perspective. You begin at a star, a tiny burst flung outward through vacuum, and you head toward Earth, travelling for hundreds, thousands, or even billions of years. But from your point of view, if such a thing existed, you never moved at all. There was no interval between the start and the end of your journey. No ticking clock, no stretching boredom, no memory of movement. You left. You arrived. That's it. It's a concept that defies intuition, and it's not because you don't understand physics. It's because our entire experience of life is stitched together by the feeling of time passing. From heartbeat to breath to blinking eye, we experience change as something unfolding. We grow, we wait, we hope, we remember. But light doesn't do any of those things. It simply is, and then it isn't. Physicists would tell you that this is because light travels at what's called null speed, a speed where the interval between 2 points in space-time becomes zero for the traveller. In space-time geometry, light's path isn't curved like ours. It's drawn like the edge of a cone, a boundary line that separates what can be influenced from what cannot. In a way, it's the pencil line that outlines causality itself. Now, that might sound abstract, and yes, in the raw math, it is. But conceptually, it means that light defines the shape of reality. It sets the rules for who can affect what, and how far the consequences of any action can ripple. The speed of light isn't just a number, It's the edge of no ability. If you turn on a flashlight in the woods, the beam pushes forward at exactly the same pace in all directions, forming a sphere that grows with time. That sphere marks the outermost limit of what that one tiny event can ever influence. Everything outside it is forever untouched by that flicker. Inside, maybe a leaf warms slightly. A moth turns toward it. A small creature blinks and scurries away. Outside, silence. Always silence. Even the stars you see in the night sky, those radiant pinpoints, each with its own ancient story, are defined by this same boundary. The starlight that reaches you has made a quiet, unwavering promise. It tells you, this is how far I've come, and no farther. If a star is too far away, its light hasn't arrived yet. To you, it doesn't exist. Not yet. Maybe it exploded 1,000,000 years ago, but you won't know until its light catches up. The universe doesn't show itself all at once. It reveals itself at the speed of light, moment by moment, layer by layer, like letters arriving slowly through a vast interstellar mail system. No message delivered before its time. And if that wasn't strange enough, consider this. When you move toward a source of light, its frequency shifts upward. It appears bluer. When you move away, it shifts downward. It appears redder. This effect, known as the Doppler shift, tells astronomers which galaxies are rushing away from us and which ones drift a little closer. It's the reason we believe the universe is expanding. Most galaxies are redshifted, meaning they're heading away from us, as if space itself is stretching. But even in this cosmic expansion, light remains untouched. It still travels at the same pace. The space between things grows, but the light doesn't change its stride. It stretches, yes. It cools, yes. But it never slows down. It doesn't adjust. Instead, the entire structure of space-time bends to accommodate its rhythm. That's why Einstein's work was so revolutionary. When he realized that the speed of light must remain constant for everyone, he saw that space and time couldn't be fixed. They had to bend. They had to become flexible, fluid dimensions that stretch and twist and dilate, just so that light could keep its perfect tempo. It's like the universe is a great orchestra, and light is the metronome. Not the loudest sound, not the most complex, but the one beat that never falters. Everything else follows it. Every galaxy, every motion, every heartbeat, each keeping time in their own way, but never faster than that tick. And in this strange geometric symphony, you too are a player. When you walk, when you speak, when you think, you're operating on the stage light defines. You can't escape it, can't cheat it, can't outrun it. But you can listen, you can reflect, you can watch the way light draws shadows, tells stories, and reveals secrets millions of years after they were whispered. Light doesn't need to rest, but you do. So tonight, as your eyes adjust to the dark and your mind drifts gently towards sleep, know this: the light that bounces off your walls, the glow from distant stars, the gentle flicker of your screen, all of it has travelled impossibly far without ever aging a single second. It is here now, and only now, just like you. The heartbeat of the cosmos and the breath of your quiet night, meeting, briefly, in the same silent room. You might not think much about it when you're watching headlights blur by on a highway, or when two planes cross each other's paths high above the clouds. Speed feels so relative in daily life. You go faster than a bicycle, slower than a jet, much slower than the International Space Station. And so, you might imagine that if you keep adding speed, if you keep going faster and faster, you might one day catch up to a beam of light, maybe even pass it by, wave at it as it falls behind you. But you can't. Not ever. This isn't a matter of technology or engineering. It isn't about propulsion or power or some future civilization learning how to break the limit. It's more fundamental than that. The speed of light isn't like a traffic rule, it's like the shape of space itself. It's not a suggestion, it's woven into the fabric of how reality works. Light moves through a vacuum, an empty stretch of space, with a speed of exactly 299,792,458 meters per second. Not roughly, not approximately, exactly. And most remarkably of all, that number stays the same no matter who is measuring it or how fast they're moving. That defies common sense, doesn't it? If you're walking on a moving sidewalk in an airport and you throw a ball forward, the ball's speed is your walking speed plus the speed of your throw. We're used to speeds adding, but that logic fails completely when it comes to light. If you're drifting in space, floating serenely, and you shine a flashlight, the beam moves away from you at that same constant speed. And if someone else is zipping past you at a third the speed of light and shines their flashlight in the same direction, their beam also moves away from them at exactly that same speed. From both points of view, the light is travelling away from its source at 299,792,458 meters per second. It's not that light is doing something strange. It's that space and time are. To preserve this fixed speed of light, the universe has to bend its own rules. And so it does. Time stretches, distances shrink. Events that might seem simultaneous in one frame don't line up in another. The structure of reality, space, time, motion, contorts itself to ensure that light never disobeys. This is the heart of special relativity, the quiet revolution Einstein gave us. He wasn't trying to make things complicated. In fact, he was trying to preserve something simple, that the laws of physics are the same for all observers. And to do that, he had to accept that time and space were not absolute. They were flexible, malleable, dependent on perspective. This is where something called the Lorentz transformation comes into play, not as a formula to memorize, but as a poetic idea. When one observer moves very fast relative to another, the coordinates of time and space must shift in just the right way to keep the speed of light constant. It's like tuning two instruments to different keys, and yet both still playing the same melody. Imagine for a moment that you're travelling near the speed of a light. You're not going to reach it, because you can't, but you're getting close. The universe around you begins to change ahead of you. The stars shift in colour. The world contracts, squeezing in the direction of motion. Your own time slows down, not for you, but from the point of view of someone watching you fly past. It's not an illusion. It's not a trick. It's a real change in the structure of reality caused by motion alone. And why can't you reach the speed of light? Because as you accelerate, your mass, your resistance to further acceleration, effectively increases. The faster you go, the harder it becomes to go just a bit faster. More and more energy is needed to add even the tiniest bit of speed. And at the limit, the exact speed of light, you would need infinite energy. The climb becomes vertical. The cost becomes infinite. The road disappears. Photons don't have that problem because they don't have mass. They're born into the universe already moving at the limit. They don't accelerate up to it. They don't resist. They simply are. There's something quietly humbling about that. We're made of matter, complex, slow, bound by inertia and curves and momentum. Light is not. It cuts through the silence, reaching from one point to another without ever stopping to exist in between. That's why light becomes more than a phenomenon. It's a boundary, a whisper from the universe that says, you may approach, but you may never cross. And so, instead of arguing, the universe reshapes its very fabric. Space bends, time slows, simultaneity slips, all to let that whisper remain unchanged. We tend to think of speed as a way to move through space, but near light, speed becomes a way to move through perception. Two people watching the same event moving at different velocities won't agree on what happened first, or whether things happened at the same time at all. That idea that simultaneity is relative grows directly from the constancy of light. What light gives the universe, more than brightness, is structure. A speed limit, yes, but also a common thread. You can measure distances in light years. You can trace histories through redshifts. You can define the visible universe not by what exists, but by what has had time to reach you. Light has no choice but to travel at that speed. You, however, have the luxury of pause, of reflection, of stillness. Tonight, while photons streak from galaxies unimaginably far away, you are resting in a moment that is uniquely yours, spun into being by your motion, your gravity, your light. The cosmos may have a speed limit, but your thoughts, your dreams, your quiet wandering through ideas, they're unbounded. Time, for most of us, feels constant. We wake up, we stretch, we measure days in coffees, in conversations, in quiet sighs by windows. We know time has passed because something changed. The bread has risen, the shadows moved. We grew older without noticing it. But that sense of time, as steady, reliable, universal, is not how the universe works. It is only how we experience it here, under the slow pull of Earth's gravity and the soft pace of human motion. Time, in truth, is not fixed. It is not the same for all. It bends, it stretches, and when you begin to move quickly, especially near the speed of light, it no longer behaves the way you expect. This bending of time is known as time dilation, and while it may sound like a thought experiment, something nestled deep in abstract equations, it's very real. It happens all the time. Your phone's GPS system wouldn't work without correcting for it. Your own body, right now, is experiencing it at tiny level compared to someone standing on a mountain. Time, you see, runs slightly faster higher up. Not because the clock is broken, but because gravity is weaker there, and time flows a little more freely. But motion also affects time, and in a much more dramatic way. Let's imagine a pair of twins. They grow up together, side by side, their birthdays marked by matching cakes and candles, their memories intertwined. One day, one of them boards a spaceship, a vessel capable of reaching speeds close to that sacred limit, the speed of light. She waves goodbye, the engines roar, and she disappears into the stars. To her, the journey might feel like a few months, maybe a year. Her clock ticks normally. She eats, sleeps, writes letters home. But when she returns to Earth, something astonishing has happened. Her twin is older, not just a little, but significantly. Wrinkles have deepened. The world has changed. Decades might have passed. This is not magic. It's not science fiction. It is a direct, measured consequence of moving quickly through space. The faster you move, the more slowly your time flows compared to those who remain still. And not just feels slow, is slow for real. The difference is measurable, concrete, immutable. Physicists describe this difference using two ideas: proper time and coordinate time. Proper time is the time experienced by you, the traveller. It is the time on your own watch, the one strapped to your wrist. Coordinate time, on the other hand, is the time seen from an outside observer's perspective. It is how someone else would describe your journey using their frame of reference. So, if you're flying through space at incredible speed, your proper time moves at a normal pace. You don't feel anything strange. But from Earth's coordinate time, your clock is ticking slower. Your heart beats more slowly. Your cells divide more slowly. Your life, viewed from a distance, is unfolding in slow motion. And this isn't theoretical. We've tested it. High-energy particles called muons are constantly raining down on Earth, created in the upper atmosphere when cosmic rays collide with molecules in the air. Muons decay incredibly quickly, so quickly in fact that they shouldn't be able to reach the ground before disappearing. And yet they do. Why? Because they're moving so fast that time dilates for them. From their perspective, they're living just as briefly as always. But from our view, their clock has slowed, giving them more time to complete the journey. A similar thing happens with astronauts. The International Space Station orbits Earth at about 28,000 kilometers per hour. That's fast, but nowhere near light speed. Even so, time moves more slowly for those astronauts. Not by much, fractions of a second, but enough to be real. Technically, when they return, they are a tiny bit younger than they would have been had they stayed on Earth. Their lives stretch just a little more slowly, carved slightly differently by the rhythm of the universe. It's as if time is a fabric, and the faster you move across it, the more it resists, not in anger, not in punishment, but in grace. It gives you a longer breath, a slower heartbeat, a quieter unfolding of moments. From the outside, you appear suspended, moving through syrup, your life stretched across more of their time than of yours. And it's worth noting, this effect is not symmetrical. If you fly away and return, you experience less time than the person who stayed. But only one of you accelerated, turned around, changed direction. That breaking of symmetry is what locks in the difference. It's why the travelling twin ages less, even though both experience time as normal in their own frames. There's a softness to this idea when you sit with it for a while. That time is not one universal river we all drift along together, but a collection of streams braided and varied, flowing at different speeds depending on your path. You and I right now may already be moving through time at slightly different rates, not enough to notice, but enough to matter. You are, in this very moment, living your own version of now, and if someone were moving quickly enough, fast enough to rival light, they would see a different slice of this moment. Their now might not include this room, might not include this you. The present is not a single plane stretched across the cosmos. It is layered, flexible, relative. So when you sit quietly in the evening and think back to your childhood, or forward to a distant future, know that time is not some perfect grid ticking away identically for all. It is a personal rhythm, a local phenomenon, and the faster you move, the more that rhythm begins to dance differently. You may never reach the speed of light, but even in your stillness, time carries you gently forward, and perhaps that is enough. There's a story you've likely heard, perhaps in a classroom or in a quiet science documentary. An apple falls from a tree. It hits the ground with a soft thud, and somehow, that moment leads to one of the greatest revolutions in our understanding of the world. Isaac Newton saw that falling apple and wondered, why does it fall down? Why not sideways or upward? What is this mysterious force that pulls things toward Earth? And so, gravity was born, not the phenomenon, but the explanation. Newton imagined a force stretching invisibly between objects, acting instantaneously across vast distances. A silent tug from one mass to another, guiding planets around stars and apples toward the dirt. For centuries it worked. It explained the orbits, the tides, the very structure of the solar system. But Newton's universe, though elegant, had a flaw. It couldn't explain why gravity existed, only how it acted. And it couldn't keep up with light. His gravity acted instantly, but light had a speed. There was a contradiction hiding in the corners. Then came Einstein. Rather than imagine gravity as a force, he offered something stranger, and somehow more beautiful. He suggested that mass doesn't just sit in space, it shapes it, warps it, stretches it. Massive objects don't pull on smaller ones. Instead, they create curves in the fabric of space and time, and those smaller objects simply follow the paths laid out for them. This idea that gravity is geometry transforms how we think about the universe. Imagine stretching a sheet of soft fabric. Place a heavy ball in the middle. The sheet sags, dips, curves inward. Now roll a smaller marble across the surface. It doesn't move in a straight line. It spirals, arcs, or even falls inward, not because the larger ball pulled on it, but because the sheet itself told it which way to move. This is how gravity works in Einstein's world. Space isn't a passive backdrop. Time isn't a steady beat in the background. Together they form a four-dimensional fabric, space-time, that bends around anything with mass or energy. And objects, whether they are comets or photons or you or me, follow the straightest possible path through this curved terrain. Here's where it gets even more surprising. Light, which we once thought of as pure and untouchable, also follows these curves. Even though it has no mass, it responds to gravity, not by slowing down, but by bending its path. It falls not like a rock, but like a ray slipping sideways along a slope. When light passes near a massive object, like a galaxy or a black hole, it arcs ever so slightly. To us, it appears to come from a different direction. This is called gravitational lensing, and it allows us to see things far behind stars, as though space itself had become a lens. Through gravitational lensing, we've seen galaxies hidden behind others, distorted into rings and arcs. The light from these distant sources left its origin billions of years ago, but it travelled not in a straight line, but along the curved ridges of space-time. It obeyed the geometry written by stars and dark matter, and the structure of the cosmos itself. Think of that for a moment. A single beam of light, quiet and constant, navigating the invisible terrain of a warped universe, not because something pushed it, but because space itself was no longer straight. That beam tells a story not just of distance, but of shape. The light we see is the shape of gravity made visible. Einstein predicted all of this in equations drawn from pure thought, long before telescopes confirmed it. The idea that light could bend around the sun was first tested during a solar eclipse in 1919. The starlight from behind the sun shifted just enough to be noticed, a ghostly nudge in the sky, and Einstein's vision was suddenly more than theory. It was a new way of listening to the universe, so when we speak of gravity now, we no longer mean a force pulling downward. Instead, we speak of dips and curves, of shapes and slopes. The Earth doesn't tug at the moon. The moon follows the natural path laid out by the Earth's curved presence. You don't fall when you trip. You continue in a straight line, but that line is curved, pulled gently downward by the shape of space-time near our planet's mass. Even the experience of weight is not what it seems. You feel pressed into your chair, not because Earth is reaching up to grab you, but because the chair prevents you from following your natural path through the curve of space-time. Without the floor beneath you, you would float, moving along the shape space as set for you. It's not so much that you're being pulled downward, but that you're being stopped from moving forward on the curve the Earth has written in the fabric around you. And all of this intricate dance of curvature and motion, emerges from one simple idea. Mass tells space how to bend, and space tells mass how to move. That's general relativity. Not a new force, but a new story. And like all stories in physics, it is best understood not just through equations, but through quiet reflection. Through watching how light curves around corners it should not reach. Through wondering why the moon continues in its endless path. Through feeling your own weight as something more than a downward force, as a clue that space and time are not quite as flat as they seem. So tonight, as you lie still and let the weight of the day settle gently around you, remember this. Gravity is not a pull. It is a path. You're resting not at the bottom of a well, but along a gentle slope in the geometry of everything. You're lying in a curve carved by the Earth, held there not by force, but by the quiet agreement between mass and space, between time and your heartbeat. And above you, light is still bending, tracing that shape, echoing the contours of a story written not in words, but in curves. Imagine, for a moment, standing at the edge of a high mountain. The wind is crisp, thin, and cool. The Earth curves ever so slightly beneath you. Far below, The world continues in its quiet, everyday motion. Cars moving like toys, rivers tracing their ancient roots. You take a breath, slow and deep, and without realizing it, in this place above the clouds, you have just stepped into a slightly faster version of time. Not by much, just a few nanoseconds faster than those standing at sea level, but faster all the same. You see, in Einstein's universe, time does not flow evenly. It moves differently depending on where you are, how fast you're going, and, perhaps most subtly, how deeply you sit in a gravitational field. The stronger the gravity, the more time slows down. The closer you are to the mass of the Earth, the slower your clock ticks. This phenomenon is called gravitational time dilation, and while it may sound like something reserved for black holes and cosmic dramas, it is quietly at work in your everyday life. It is happening right now, while you sit, while you sleep, while satellites drift above you, tracking your location with eerie precision. Let's begin with something simple: the GPS in your phone. Every time you open a map, ask for directions, or watch a little blue dot crawl along a road, you're relying on a constellation of satellites orbiting the Earth about 20,000 kilometers above your head. Each of these satellites contains extremely precise atomic clocks, ticking away the seconds with astonishing accuracy. But here's the twist. Those clocks aren't ticking at the same rate as the clocks on the ground. Because they are farther from the centre of Earth's gravity, time moves slightly faster for them. And because they are moving quickly in orbit, at around 14,000 kilometers per hour, special relativity says time should also move slightly slower. These two effects, gravitational dilation and motion dilation, pull in opposite directions, but gravity wins. The net result is that GPS clocks in space tick about 38 microseconds faster per day than clocks on Earth. That may not sound like much, but in the world of GPS, where location is calculated by the precise timing of signals, even microseconds matter. Without adjusting for these relativistic effects, GPS readings would drift by several kilometers each day. You'd miss your turn. Your rideshare driver would appear to teleport across town. Planes would veer off course. Every navigational system we rely on would gradually unravel. So, engineers do something quietly brilliant. They build the corrections into the system. They factor in Einstein, not as a decoration, but as a requirement. Your phone's blue dot stays on the street, not because of a signal, but because of a century-old insight. That time itself is flexible. And this isn't limited to satellites. Even on Earth's surface, height makes a difference. At the top of Mount Everest, time runs faster than it does at sea level. Again, the difference is tiny, just fractions of a second over the course of a lifetime. But it's there. If you were to live your entire life on a mountaintop, and your twins stayed at the beach, you would age ever so slightly faster. You would experience more time, not by feeling it, but by accumulating it. There's something almost poetic about that. The idea that mountains don't just rise, they lift you out of time's deeper pull, that living closer to the sky is, in some quiet way, an act of acceleration through time. But let's bring it even closer. The Earth is not a perfect sphere. It bulges at the equator and flattens slightly at the poles. This means that gravity is a little stronger at the poles than at the equator, and that means, yes, time ticks a little more slowly for someone living near the Arctic Circle than for someone living near the equator. Your latitude isn't just a coordinate, it's a temporal address. You might be wondering, do these differences matter to us really? Aren't they too small to change anything in our lives? On one level, yes, they're imperceptible, but on another level they change everything. They remind us that time is not a shared drumbeat. It is a network of rhythms, each slightly different, each dependent on where and how you exist. The world is not synchronized. It is in a gentle, shifting harmony. And more than that, these differences offer a kind of quiet reassurance. They say, the universe is paying attention, not just to stars and galaxies, but to your place on a hillside, to the path of a plane, to the altitude of a cabin tucked in the Alps. Time flows not in one great river, but in countless streams, each bending, curving, speeding or slowing, depending on the weight of the world beneath them. It's not just science, it's softness. It's the awareness that even time has texture. So the next time you stand on a hill, or ride an elevator to a higher floor, or fly in a plane above the clouds, remember, you're moving through slightly different time. You're seeing the world not just from a new height, but from a new tempo. The universe, in its quiet precision, is allowing you to drift just a little farther into the future. And you don't need to feel it for it to be real. You just need to know it's there, like a slow exhale beneath all the rushing noise of life. You are at every moment not just where you are, but when you are. And the shape of the earth, the height of your bed, the mountain beyond your window, all of it plays a role in how time chooses to unfold around you. And maybe, just maybe, that unfolding is a kind of gift. Imagine two children, twins, born under the same sky, moments apart. They grow up side by side, climbing the same trees, arguing over the same books, laughing at private jokes that no one else would understand. They measure time together. First steps, first words, first heartbreaks. Every candle blown out is shared. Every scar, every birthday, every story, woven into the same rhythm. And then one day, something changes. One of them, curious, brave, restless, climbs into a spacecraft, a vessel designed to graze the edge of possibility, moving fast. Not highway fast, not jetliner fast, but nearly the speed of light. A speed so close to that universal boundary that the stars ahead no longer twinkle, but compress into a blue-white blur. She leaves the Earth, and her twin, behind, not out of distance, not out of anger, but for a journey that will take her through both space and something stranger, time itself. From her point of view, the trip is simple. She accelerates gently, drifts steadily. Maybe there's a notebook on board. Maybe she writes, reads old letters, thinks of home. Her clock ticks forward, just as it always has. Each minute feels like a minute. Each breath follows the last. But something strange is happening, and she can't feel it. Not directly. Because back on Earth, time is flowing differently. The twin who stayed behind lives through decades, watches cities rise and fall, friendships come and go. She grows older, quietly. Perhaps she walks by the launch site now and then, tracing the place where her sister left. Perhaps she keeps the same mug, the same worn sweater, the same memories. And then, one day, the spacecraft returns. Out steps the traveller, younger, maybe not unchanged, but undeniably less aged. Her eyes carry the same memories but not the same number of days. She's still the sister who left, but now standing beside someone who has lived more time, seen more dawns, read more calendars. This is the twin paradox. And though it may feel like fiction, like some dreamy metaphor about distance and aging, it's not. It is a real prediction of special relativity. When you move at speeds near the speed of light, time slows down for you. Not metaphorically, not just in theory, objectively. Your clock ticks more slowly compared to someone who's not moving that fast. And not just your clock, but everything about you, your heartbeat, your thoughts, your aging. From your point of view, you're living normally. From the other's point of view, you're stretching through time more slowly. But why do the twins age differently? Aren't all motion-based effects supposed to be relative? Here's where the subtlety comes in. The twin who left Earth wasn't just moving at high speed, she also accelerated, turned around, and came back. That acceleration breaks the symmetry. It distinguishes the traveller's frame from the one who stayed. It's not just relative motion. It's a change in reference frames. And in that change, in that turning point, the universe recalculates. It says, this path was longer in space, but shorter in time. Acceleration in this case isn't like pressing the gas pedal. It's more like choosing to come back, choosing to reconnect. And the consequence of that choice is that time unfolded differently. We've tested this idea, not with twins exactly, but with particles. In particle accelerators, muons, tiny unstable particles, move at nearly the speed of light. On Earth, they decay quickly. But when they're moving fast, they live longer. Their internal clock slows, and when they finally decay, they've existed for far more of our time than of theirs. It's the same with astronauts on long-duration space flights. The difference is tiny, but measurable. The faster and farther they travel, the less time they experience compared to Earth. The twin paradox isn't just a thought experiment. It's a glimpse into how time is deeply, inherently tied to motion. There's something quietly emotional about this too. The idea that two people, once so synchronized, can live through different amounts of time, not because of choice or fate, but because of speed. That one can return to find the other older. That stories can diverge in time, even when the heart remembers the same place. But maybe that's the most human part of it, because we do live different durations, even now. A minute waiting in a hospital feels longer than one laughing with a friend. A week in grief feels stretched and tangled. A year of joy might vanish in a blink. Our emotional clocks are not synchronized. We live relativity in our own, quiet ways. The twin paradox is just a more precise physical version of something we already know deep down. That time is not just numbers on a calendar, it is lived, and living changes it. So perhaps the traveller, stepping out of her craft, doesn't mourn the years lost. Perhaps her twin doesn't envy the youth returned. Perhaps instead they sit together on a bench, drinking tea, watching the same sunset, each in their own time, each in their own rhythm. And the story is not about who aged more. It's about how the universe allowed both paths to be real, and how reunion is always possible, even if the clocks disagree. There's something comforting about the idea of now. You think of it as a shared moment. The second hand ticking the same for everyone. The same breeze brushing across cities and oceans. People sipping tea in different time zones, but all existing under one unified present. But the universe doesn't agree. What we call now is not a single, universal slice across all of space. Instead, it's local, personal, dependent on how you're moving, where you're standing, and what you're near. Einstein's theory of relativity doesn't just tell us that clocks can tick at different rates. It tells us that the present itself can shift and warp depending on your point of view. It begins subtly. Imagine two people standing on a platform as a train rushes past. There's a light at the centre of the train car. From the point of view of someone on the train, that light travels equal distances to both the front and the back. It splits and reaches both ends at the same time. But someone watching from the platform sees something else. Because the train is moving forward, the light travelling toward the back has less distance to go, while the light heading forward has more ground to cover. So to the observer on the platform, the light reaches the back wall first. Who's right? The answer is both. Each sees a different version of simultaneous because simultaneity is relative. Events that happen at the same time in one frame may happen at different times in another. This isn't an illusion or a misunderstanding, it's a fundamental part of how space and time work. In our everyday life, moving slowly and close to Earth, these differences are too small to notice. But if you're moving close to the speed of light, or observing events light years apart, they become meaningful. Profound even. Two astronauts passing each other at high speed may disagree on the order of distant events. One might believe a star exploded before a planet formed, while the other believes the reverse. From our perspective, they can't both be right. But from the universe's perspective, there is no contradiction, because there is no absolute order to things separated by space. And that leads to something quietly astonishing. There is no universal now. You may be listening to this video in your room, thinking of someone far away, perhaps in another country, another time zone. You might feel intuitively that you're both experiencing the same moment, but from the viewpoint of physics, there is no single cosmic clock ticking across the universe. There is no grand curtain falling over the stars saying, "This is the present." Instead, the slice of time you call now is yours alone, a cross-section of space-time drawn by your motion, your gravity, your position. That idea may feel lonely at first. We like to think we're all in this together, that every breath is shared with someone else, somewhere in the same fleeting second. But maybe there's something beautiful in the individuality of time, that your present is yours, shaped by your path through the universe, that we're not snapshots in a single album, but unique threads weaving through a greater fabric, each with its own orientation and glow. It also raises gentle questions. If now is relative, what does it mean to remember? When you think of a friend who's far away, are you remembering a moment they've already lived, or one they're about to? When you gaze at the stars, you're seeing light from the past, but are you looking into a shared history, or one filtered through your own trajectory? Even communication becomes poetic. A message from a distant satellite bouncing across the cosmos is never perfectly current. It arrives not just from far away in space, but from a different slice of time, a whisper from a different now. And yet, despite all this relativity, we still connect. We still fall into rhythm. We still share lives and build memories and say things like, "at the same time," not because the universe guarantees simultaneity, but because our hearts do. There's a quiet resilience to that, a kind of human gravity that pulls us together, even when space-time insists we are not perfectly aligned. In the vastness of the cosmos, where there is no objective present, no single thread of cause and effect, it is our intention that gives moments meaning. It is the care we place in an action, a thought, pause, that anchors it. It is not when something happened in the universe that matters most, but when it happened for you and what it meant. So if you've ever looked up at the night sky and wondered if someone somewhere was looking up at the same time, maybe they weren't. Maybe their now was a little earlier, or a little later, or angled through a different curvature of time. But they were still looking, and in that act, separated though you may be by light years and velocity, a connection is formed. Not through simultaneity, but through shared curiosity. Perhaps in that sense the universe does offer a kind of now, not fixed in physics, but in feeling, and now defined not by equations, but by empathy. So as you lie back and feel the slow ticking of your own internal clock, know that this moment, this now, is uniquely yours. It does not have to match anyone else's. It does not need to. And if someone else, somewhere far away, is thinking of you right now, or perhaps 5 seconds from now in their frame, it still matters. Because in the end, it is not where or when we are that defines connection. It is the act of reaching. Imagine, for a moment, chasing light. You stretch your limbs, fire your engines, accelerate through empty space. You go faster, faster still, until stars begin to distort and the field of vision narrows to a tunnel of streaking light. Every burst of energy you add moves you a little closer to that sacred limit, 299,792,458 meters per second. But no matter how much you try, how much you burn, light always stays ahead. Unreachable, unyielding. It's like trying to catch a shadow that's not cast from behind, but from infinity itself. There is no catching up, not because we're not clever enough, or because we haven't yet built the right machine, but because the very shape of reality forbids it. The faster you move, the more energy you need. At first it's manageable, a bit more fuel, a bit more force. But then something strange happens. The resistance grows, it becomes exponential. You start pouring in energy not to go faster but just to stay close, and as you approach the speed of light, the math delivers a quiet verdict. You'd need infinite energy to reach that final pace. Infinite. A word that doesn't just mean a lot but a boundary with no shore. Why does the universe set such a limit? Perhaps it's because light isn't merely fast, it's foundational. It defines what can touch what and when. It gives shape to the possible and outlines the edge of causality. It's not a racer, it's the ruler. Still, physicists have wondered, what if there was something faster? What would it mean? Not just practically, but philosophically. Enter a peculiar idea, the tachyon, a particle that, from the very moment of its creation, already travels faster than light. It doesn't accelerate to that speed, it was never below it. Tachyons are not part of our known reality. No one has ever seen one. But mathematically you can write them down, you can imagine how they'd behave, and what you get when you do is a particle that seems to run backward through time. If light is the horizon, tachyons are already over the edge, sprinting in reverse. They are strange, not because they are merely fast, but because they invert the relationship between cause and effect. From some perspectives, a tachyon could arrive before it was emitted. A detector might register it before the particle had even been created. It's not just a question of when something happened, it's a breakdown of what it means to happen at all. In a normal world, you light a candle, and then the room glows. You speak, and then someone hears. But with tachyons, the response might arrive before the question. The flame might flicker before the match is struck. The glow precedes the gesture, a future cause pulling its own past into place. Of course, all of this exists only in theory. Tachyons haven't been observed, and perhaps never will be. But the thought experiments they inspire are more than idle curiosity. They test the boundaries of how we understand time, information, and what counts as reality. Because it's not just about speed anymore. It's about the architecture of causality. And that architecture, for all its complexity, is fragile. Light speed is not just a speed, it is a wall. Behind it, the universe preserves its sequence. Events unfold. Causes lead to effects. Things follow things. But beyond it, the rules begin to bend, then twist, then break. Physicists sometimes call these ideas unphysical, not because they're offensive to the senses, but because they imply logical contradictions. A tachyon might allow you to send a signal to yourself before you sent it. It might allow an event to unhappen or to cause itself. The very notion of a timeline begins to blur into a loop, and here's the heart of it. The speed of light is not sacred because of how fast it is. It is sacred because it preserves the story. It keeps before and after from swapping places. It protects memory. It maintains the shape of cause and effect. So when people ask, why can't we just go faster than light? The answer is not, because we haven't built the right rocket. The answer is, because speed beyond that point isn't speed anymore. It's a cut in the fabric of time itself. It's a gentle limit, written not in warning signs, but in paradoxes. If you try to cross it, reality no longer agrees with itself. That doesn't mean we stop imagining. The edges of understanding are always strange, and sometimes the best way to learn is to ask, what would break if this were true? That's what tachyons offer. Not a blueprint for new technology, but a mirror. One that shows us how closely time, space, speed, and sense are all entangled. Even imagining a forbidden speed tells us something important, that there is a logic to the universe, quiet and consistent, threading through everything, and sometimes simply trying to outrun it reminds us how precious it is. So tonight, as you rest under a sky lit by photons that never aged on their way to your eyes, know this. You're surrounded by stories that obey the light. The flickers from distant stars, the warmth from a friend's message, the echo of your own heartbeat. They all arrive in order, one after another, like notes in a song. And faster than light? That's a dream the universe won't permit. Not because it's cruel, but because some dreams unwrite the page they're drawn on. Let's try something that feels innocent enough. Imagine you send a message, a simple one. Maybe it says hello, maybe it's just a number, a flicker of light, a gentle pulse across space. You send it to someone far away, moving relative to you at high speed, and then, strangely, unexpectedly, they receive the message before you sent it. Not metaphorically, not "it feels like" or in their time zone. Actually before. From their perspective, the reception came first, and if they reply right away, just as fast, just as carelessly, it's possible that you receive their reply before you sent the original message. You sit there, looking at a response to a question you haven't asked yet. This is the unsettling heart of what happens if faster-than-light communication becomes possible. Not merely faster-than-light travel, not spaceships zipping through galaxies at superluminal speeds, but the ability to transmit information across space at a rate that outruns light itself. It's called the tachyonic antitelephone, a thought experiment born from the idea of tachyons, those hypothetical faster-than-light particles we met in the last session. If tachyons can carry messages, and if observers are moving relative to each other, then with the right setup signals could arrive before they were sent. It sounds like magic. But the math, if taken literally, permits it. The consequences are not just weird, they're devastating. Because if you can send a message into the past, even by a few seconds, then causality begins to unravel. You can warn yourself not to send the message. You can tell a friend not to start the engine, not to leave the house, not to make that call. You can respond to actions that have not yet occurred, and by doing so, you might prevent them from ever happening. This is more than a philosophical quirk. It's a logical crisis. Take, for example, the well-known grandfather paradox. Suppose you could travel back in time and prevent your own grandfather from meeting your grandmother. By doing so, you prevent your own birth. But then, if you were never born, who went back to interfere in the first place? The contradiction loops endlessly. With faster-than-light messaging, similar paradoxes arise. They may be smaller in scale, no time machines, just small reversals of order, but the principle is the same. If an effect arrives before its cause, then the sequence breaks. The story contradicts itself. And physics, like storytelling, depends on consistency. So what does the universe do? It protects itself, not with alarms or firewalls or sudden thunderclaps, but with a simple rule: nothing can go faster than light. Not because the speed itself is dangerous, but because the structure of reality depends on events remaining in order. Causality is not just a guideline, it's the spine of every process. You strike a match, and then fire begins. You fall, and then you hit the ground. You speak, and then the echo returns. The elegance of the cosmos lies not only in its size or age, but in this quiet obedience to order. Faster-than-light travel or communication threatens that order. It lets echoes arrive before the shout. It invites a kind of temporal chaos, not just backwards time, but impossible loops. Messages that erase themselves, choices that cannot be made because their consequences preempt them. Some physicists have tried to patch the problem. Perhaps the universe would forbid contradictions. Perhaps only certain backward messages could be allowed, ones that somehow fit, that don't cause paradox. These are the basis of self-consistency conjectures, that whatever happens must happen in a way that doesn't undo itself. But even then, we're left with a universe tightly coiled around its own history, where freedom of action becomes an illusion and every event is already folded into a loop that cannot be altered. It's an unsettling place, beautiful maybe, but eerie. And so, most physicists agree. Even if faster-than-light particles can be written into equations, the world we live in is not built to accommodate them. The universe seems engineered to protect causality, not with brute force, but with elegance, with speed limits, with time dilation, with the quiet refusal of reality to tangle itself. We don't know for certain why the laws of physics are this way, why the speed of light is what it is, why space-time bends as it does. But we can say this: those laws preserve meaning. They keep the story from folding in on itself. because at the heart of every action is a memory of what came before. You eat because you felt hunger. You knock because you want someone to answer. You dream because of what you've lived. The cause and effect nature of existence isn't just scientific, it's emotional. It's how we build identity. A future that arrives too early, a past that won't stay put. These are not just violations of logic, they are violations of self. So the next time you wonder about faster than light travel or messages from the future, know that the boundary isn't just physical, it's philosophical. The universe, in its deep quiet, insists that the arrow of time moves forward, not with force, but with grace, not to imprison you in the present, but to give meaning to choice, to make sure that when you say something it wasn't already said, that when you move forward, it is into something genuinely unknown. And as you drift towards sleep tonight, know this: the stars above you are still sending their light. That light travels forward, moment by moment, never faster than it should, never out of order. It arrives not too early, not too late, but precisely when it means to, and perhaps so do you. Imagine holding a sheet of paper. On it, you draw two dots, one at the top left, the other at the bottom right. The shortest path between them you might think is a straight line, but then you do something curious. You fold the page so that the dots touch. Suddenly distance disappears. What was once a long walk is now a single touch. This is the metaphor often used to describe a wormhole, a hypothetical bridge, sometimes called an Einstein-Rosen bridge, that links two distant points in space-time not by crossing the terrain, but by bending it. The idea first emerged from general relativity itself. When Einstein and his colleague Nathan Rosen examined the equations of gravity, they found something unexpected: mathematical solutions that connected 2 points, not by a path through space, but through a hidden tunnel. These wormholes, as they came to be called, weren't inserted into the theory. They were already there, waiting to be noticed. At first, they seemed like cosmic curiosities, theoretical bridges possibly linking different parts of the universe, or even different universes altogether. But these early versions weren't practical. They pinched off too quickly, collapsing before anything could pass through. They were like doorways painted onto walls, beautiful but impassable. Then came a twist. Physicists began to wonder, could a wormhole remain open if held in place by something strange? Exotic matter. Not matter that glows or burns or weighs heavily in your hand, but matter with negative energy. Something that doesn't pull things in like gravity but pushes them away. A repulsive pressure that stretches space rather than squeezing it. Negative energy isn't a complete fantasy. In quantum physics, there are hints of it, seen in effects like the Casimir force, where empty space between two plates exerts a subtle push. But to stabilize a wormhole, you'd need a significant amount of this elusive substance, more than we've ever measured, more than we know how to create. Still, the math says, if you had the exotic matter, then you could, in theory, build a traversable wormhole, a tunnel through the fabric of the cosmos, not just a shortcut in space, but possibly a shortcut in time. Here's how. Suppose you construct a wormhole between two rooms. Then, you take one end of the tunnel, just the mouth of it, and you move it. Perhaps you put it on a spaceship, fly it around at high speed, and then bring it back. Because of time dilation, that end of the wormhole has aged more slowly than the one you left behind, so now the two ends are connected through space, but also through different times. Step into one, and you emerge from the other, not only elsewhere, but elsewhen. You've built a time machine, not by violating the laws of physics, but by gently following them to a very strange conclusion. And yet, everything about this remains speculative. No wormholes have been observed. No exotic matter has been captured in jars or measured in labs. These are not devices waiting in secret hangars. They are solutions, mathematical constructs within the equations of general relativity, given meaning by our imagination, and our hope that reality might sometimes surprise us. But even if we never build a wormhole or walk through one, the idea still tells us something beautiful. It tells us that the universe, in its quiet complexity, contains possibilities we've only begun to guess. That space might not be as rigid as it seems. That distance might sometimes be more flexible than we think. And it tells us that time, so often thought of as a straight road, might contain corners, places where cause and effect are not quite so simple, where the future can loop back toward the past. Still, there's a gentleness to how wormholes live in our minds. They're not portals of chaos or traps of paradox. They're the product of elegant equations and speculative courage. They exist not to defy physics, but to follow it further than we've gone before. And like so many ideas in theoretical physics, their power isn't just in whether they're real, but in how they help us think differently about space, time, and what it means to journey. Because even if you never step through a wormhole, you live in a universe that allows for the question, and that might be enough. So as you rest tonight, imagine this. Far away, in some quiet corner of possibility, there might be a tunnel, silent, stable, waiting. One mouth facing a galaxy you'll never see, the other just a few feet from where you are now. The two connected not by distance, but by a shared thread in the fabric of space. A thread you could walk through in a single step, if only the universe were generous enough to open its seams. And even if it never does, the thought remains. A folded page in the book of time. There's something poetic about the idea of time as a circle. We're used to thinking of time as a line, past behind us, future ahead, and the present as a little window sliding along. But imagine, just for a moment, if that line bent gently until the ends touched. A loop, a path that leads not just forward, but back to where it began, and not only in space, but in time. This is what physicists call a closed time-like curve, or CTC. It's not a fantasy from fiction, but a real solution to Einstein's equations. A mathematical possibility that allows an object to travel along a path through space-time and eventually return to its own past. Not by jumping or skipping, but by walking. Slowly, continuously, never leaving the fabric of space-time and yet arriving somewhere it has already been. It's as if you could take a train, not a metaphorical one, but a physical one, ride it in a giant circle and step off into yesterday. Of course, there's a catch, or rather, a tangle. Let's say you do take that train, and in your pocket is a watch, nothing fancy, just a small silver one, perhaps passed down from someone in your family. You ride the curve, return to the past, and while there, you hand the watch to a younger version of yourself. That younger self carries it forward, eventually steps onto the same train, loops back in time, and gives it once more to a younger self. And now we ask, where did the watch come from? It wasn't built, it wasn't bought, it was never manufactured, never designed. It exists in an eternal loop, passed from future to past to future again. A gift with no giver, a story with no beginning. This is called a bootstrap paradox, named after the phrase, pulling oneself up by one's own bootstraps, doing something impossible by relying on yourself. In physics, it's the unsettling situation where an object or a piece of information appears to exist without origin. It just is, sustained by the loop of time. Some find this deeply troubling, others find it oddly beautiful, because in a way, it's not a contradiction. There's no moment where logic fails outright. The loop is self-contained, self-consistent. It obeys its own rules. You can trace it over and over and it never breaks. It just doesn't tell you where it starts, because it doesn't. It's closed. To make sense of this, physicist Igor Novikov proposed a principle. It's called the self-consistency principle, and it suggests that if closed time-like curves exist, then only events that are consistent with their own history can occur. You can't create paradoxes. You can't change the past in a way that would prevent your journey to the past. The timeline, in a sense, defends itself. In the world of Novikov, you could travel into the past, but anything you do there must already have been part of history. You can't stop the invention of something if your trip depends on it. You can't destroy the machine that brought you back. You can play your part, but only the part that was always meant to be played. This leads to curious stories. You write a symphony, become famous. Years later, someone brings you a score, an old dusty composition written long ago. You recognize it. It's your work. You copy it, publish it. Decades pass. The score is handed to your younger self. That's how you learn to write music. Where then did the symphony come from? It exists. It's consistent, but it floats in the loop, unpinned from origin. Like the watch, like the whisper of an idea that seems to arrive before the thought. Closed time-like curves are not easy things to build, nor is it clear they can exist at all in a universe governed by quantum rules, but their presence in the equations of general relativity tells us something important. The structure of time is stranger than we assume. It's not merely a river flowing forward. In some geometries of space-time, it's a spiral, a coil, a loop, and inside those loops, cause and effect don't disappear, they fold together. There is a softness to these ideas if we approach them gently. They don't shout, they hum, they ask us to rethink what it means for something to begin, or to end, or to happen at all. Because even outside physics, we live with loops, traditions passed down, phrases we say because someone once said them to us, stories whose authors we've forgotten, but whose meaning persists, knowledge that seems to come from nowhere, carried through generations, looping from mouth to ear and back again. Maybe time loops are not just scientific curiosities. Maybe they are metaphors for memory, for culture, for love that outlives its original sender. And so, as you drift tonight, think of the stories that never had a clear beginning, the ones that feel like they've always been with you. A lullaby, a dream, a gesture from someone long gone, passed on without origin. Not everything has to begin at the beginning. Some things just are, like time, circling quietly through itself. The more we imagine time bending, looping, or turning back on itself, the more one question begins to whisper from the edge of logic. What stops it from breaking? If time allows its own path to curl, if paradoxes can emerge from simple loops, then why haven't we seen them? Why haven't messages from the future arrived in our inboxes? Why haven't we met travellers from timelines rewritten? It's here that physicist Stephen Hawking offered a quiet, almost humorous suggestion. He called it the chronology protection conjecture, the idea that the universe, by its very nature, prevents time travel into the past, not out of malice, not because it's impossible to write such scenarios in the equations, but because the universe may intervene before things go too far. In Hawking's vision, time is not merely a passive backdrop, it is a structure with built-in resilience. Whenever a timeline is in danger of contradiction, of causality folding in on itself, the laws of physics, particularly quantum effects, begin to act like a protective current, as though the universe senses the ripple of a paradox and responds not with violence, but with instability. Imagine trying to build a time machine, perhaps a wormhole or a loop in space-time. As you near the moment of success, strange things begin to happen. Tiny quantum fluctuations, virtual particles flickering in and out of the vacuum start to amplify. At first, they're harmless, but as the closed time path stabilizes, they feed off each other. They grow, they spiral, and soon the entire structure begins to shake with a feedback too strong to ignore. The wormhole collapses, the loop unravels, the path through time closes itself off before a paradox can take root. It's like trying to whisper a contradiction into the ear of the universe, only to find that the universe raises its voice just enough to drown you out. We don't know for certain that Hawking's conjecture is true, but it fits a broader pattern in physics, that singularities, infinities, and paradoxes are not errors in our equations, but boundaries. Places where nature begins to say, "You may think, Father, but you may not go." This is echoed in another idea, cosmic censorship. It suggests that nature hides its most extreme features, like the raw singularity inside a black hole, behind event horizons, curtains of no return, boundaries where the laws still apply but our ability to observe breaks down. It's as if the universe, in all its openness, still keeps a few secrets, not to taunt us, but to keep its story coherent. Perhaps time, too, has curtains. Perhaps every timeline is draped in quiet protections, not visible to us, but woven into the very nature of causality. Like a book that can only be read forward. Like a song that must be played from the first note to the last. It doesn't mean that backward time travel is impossible in theory. Our equations don't forbid it outright, but they hint, ever so gently, that something destabilizes when you try. That nature becomes turbulent, fractal, unresolved. Think of a mirror, polished and still. When light hits it straight on, you see yourself clearly. But if you bend it, if you crack it even slightly, the reflection becomes warped, not destroyed, just disallowed. The image will not hold. Time, too, may resist reflection. And yet, there's beauty in that resistance. Because what the universe seems to protect isn't just logic, it's sequence, it's story. It's the ability to say, this came before that. Without that, meaning falters, not only in science but in memory, in choice, in love. If you could return to yesterday and undo what you did, then regret becomes meaningless. So does courage, so does growth. The possibility of pain is also the foundation of redemption. The flow of time forward is what lets action become transformation. In a sense, the universe is not denying you a time machine. It's giving you something greater, a timeline that holds together. A world in which the past cannot be rewritten, but the future can still be shaped. That may be the most generous design of all. So as you rest tonight, perhaps let go of the wish to loop back. Let the past lie where it fell, its lessons folded into the fabric of who you are now. There's comfort in a timeline that moves forward, not rigidly, but reliably. Not always gently, but always with coherence. You're not trapped by this forward flow, you are guided by it. And somewhere, beyond equations and conjectures, that may be what time truly is, not just motion, but meaning, unfolding. Far away in the stillness of deep space, there exists a boundary that does not mark a wall or a surface you could touch, but rather a limit where even light cannot return. It is called the event horizon, and to understand it is not to look at a place, but to contemplate the very edge of knowability, the place where motion becomes memory, where time itself seems to lean toward stillness. A black hole does not pull like a magnet or consume like a fire. It bends space-time so thoroughly, so gently at first, and then so overwhelmingly that all paths curve inward. Not just the paths of particles or planets, but even the trajectories of photons, those tireless messengers of light. Imagine standing far from a black hole and watching as a spaceship drifts toward its center. You see it move calmly, smoothly, drawn by gravity just as anything would be. But as it nears the event horizon, the invisible surface where escape becomes impossible, something strange happens. The ship appears to slow, not because it hesitates, but because time itself is stretching. From your perspective, the closer the ship gets to the horizon, the slower its clock ticks. The engines fire more slowly. The flicker of its lights becomes sluggish, fading toward a red, until finally it appears to freeze, suspended just above the edge, unmoving. As if caught in a photograph, a moment stretched infinitely across time. But for those aboard the ship, nothing strange is happening. Their clocks tick normally, their hearts beat. They may not even notice the horizon as they cross it, except for the disquieting realization that no signal they send ever escapes. Their radio calls fall inward, their light spirals down, the rest of the universe has drifted beyond reach. This is not science fiction. It is the calm verdict of general relativity, that the gravitational field near a black hole grows so strong that it warps not only space, but time, so profoundly that from outside the fall seems to slow into stillness, but from inside it continues like any other fall, inevitable, unstoppable, and it becomes more than a fall. The gravity is not merely strong, it is steep. If you were unfortunate enough to fall feet first into a stellar mass black hole, the difference in gravity between your feet and your head would become unbearable. Your body would be stretched into a thread, a process known, somewhat whimsically, as spaghettification. It is not painful, not in theory, not for long, because the very concept of space and time becomes distorted, compacted, twisted beyond the limits of comprehension. Yet all of that, every wild stretch, every collapsing clock, every silent spiral, is invisible from the outside. To us, the black hole remains a shadow, a dark sphere with no surface, no outline, only the event horizon, that abstract skin where light gives up its final attempt to flee. And even that horizon isn't solid. It's a threshold, a curve in the fabric of space where escape velocity becomes the speed of light. Cross it, and no path, no matter how clever, how fast, how desperate, can bring you back. So the black hole is not devouring. It's silent. It doesn't suck or roar or blaze. It waits. And light, with all its speed and determination, can do nothing but bend inward, tracing tighter spirals until it disappears. From the outside, the black hole appears timeless, an eternal dark orb, unmoving. And in a way it is, because as far as we can see, nothing ever truly crosses the horizon. Every object falls slower and slower, never quite arriving, always seeming just about to vanish. But inside, the story continues, not because time stops, but because it becomes something else entirely. What that means, we'll explore soon. For now, it's enough to know that from our perspective, yours, mine, the astronomer peering through a telescope, the black hole holds a kind of stillness that is not peace, but pause. And still, the universe remembers where it is. There are real black holes out there, thousands, likely millions, scattered throughout galaxies. Some formed from the collapse of massive stars. Some, like the giants at the centres of galaxies, may have grown slowly over eons, and yet, no matter their origin, they all share this same quiet feature, an event horizon where time dilates, where light hesitates, where the edge of observation becomes the end of the story, or maybe just the edge of our story. Because what happens next, the question of what lies within, is something no light has ever returned to tell. So as you drift tonight into sleep, imagine a beam of light tracing a graceful arc near a black hole. Not plunging in, not lost, but just close enough to feel the curvature, just close enough to bend. It circles once, maybe twice, then escapes. Not because it was fast enough, but because it stayed far enough. You too live near horizons, edges of understanding, boundaries of perception. Some you cross, some you observe from a distance, and some, like the black hole, invite you to imagine what lies beyond, even if you never follow. Not all darkness is emptiness. Sometimes it is simply the place where stories pause and light holds its breath. So what happens inside a black hole? We cannot say for certain. No signal has ever escaped. No light, no whisper, no memory drifts back to tell the tale. What lies beyond the event horizon is hidden not by fog or distance, but by the very structure of reality. Even our best theories reach for it the way one might reach for a dream just after waking. Half-formed, slipping, but still we try. Once past the event horizon, the rules of space and time continue, but they change shape. The coordinates that once described movement outward now describe time, and what once described time begins to describe a direction from which you cannot turn back. This is perhaps the strangest thing. Inside a black hole, the radial coordinate, the distance to the centre, becomes a kind of future. Not a place you fall toward, but a moment you are drawn into. Just as you cannot stop moving from one second to the next, once inside, you cannot stop moving toward the singularity. That singularity, the heart of the black hole, the mathematical point of infinite density and zero volume, a place where our equations become wild and undefined, where curvature becomes infinite, where the smooth fabric of space-time seems to tear, not in any visible way, but in the way numbers tear when they divide by zero. It is important to pause here, because we do not know if the singularity really exists. It is a prediction from general relativity, yes, but relativity is not the whole story. At extremely small scales, the quantum world begins to speak, and we do not yet have a theory that gracefully unites gravity and quantum mechanics. So the singularity is not necessarily a place, but a boundary of understanding. A sign that our tools are no longer sufficient, that we've followed the trail to the edge of the map, and the ground ahead has not yet been drawn. Some believe the singularity might be avoided, that quantum effects could smear it out, replacing it with a finite, comprehensible region of ultra-dense matter. Others suspect that black holes may bounce, or tunnel, or birth new universes in their depths. But all of that remains speculation, beautiful, haunting, hopeful, but beyond what we can observe. And so, when we say inside the black hole, what we really mean is a space disconnected from ours, not by distance, but by destiny. Once something has passed the event horizon, it cannot remain part of the universe we know. It becomes part of an interior, a region governed by its own future, a future that always ends at the singularity. It is not violent in the traditional sense. You do not fall faster and faster in the way a stone falls from a cliff. Time continues, your thoughts may continue, your heartbeat ticks. But the direction of time now leads inward. There is no path back. Not because something pushes you forward, but because there is no back to go to. Time and space switch roles. Outside the black hole, you could choose a direction. You could stay still or turn around. Inside, there is only forward, and forward is toward the centre. This inversion is not easy to imagine. Most metaphors fail. It is as if you were caught in a river, but the river is not water. It is time itself, pulling all things inward not by flow, but by inevitability. And what lies at the end of that flow? That is the question we cannot yet answer. Perhaps a true singularity, perhaps something else. Perhaps, as some propose, information itself undergoes a transformation, folded, encrypted, preserved in ways we have yet to grasp. The important thing is not to treat the black hole's interior as merely destructive. Yes, the gravity is immense. Yes, it erases the outward path. But what lies within might also be a continuation, a process, a place where known physics ends, but not necessarily existence. The interior of a black hole is not empty. It is filled with everything that fell in, with all the mass and memory, all the history and light that once moved freely in space. You might imagine it like a cathedral with no windows, still, silent, unlit from the outside, but still full of structure, of echoes, of weight. So when we say something has been lost to a black hole, perhaps that is only partially true. It is lost to us, but it is not gone. It has crossed a boundary. It exists still, just not in any way we can reach. And perhaps that's what makes black holes feel so mysterious. Not their darkness, but their solitude. They are regions of the universe that remember everything and share nothing. Tonight, if your thoughts begin to drift towards silence, imagine not absence, but a quiet interior. A space where time does not stop, but flows in one direction only. A place where space narrows into inevitability, not as punishment, but as a whisper from physics that there are still places we cannot follow. Not yet. And maybe, one day, we will. Until then, black holes remain the shadows that watch the stars. And inside their silence, time folds into something we've yet to understand. If nothing can escape from a black hole, not light, not sound, not even gravity in the traditional sense, then it would seem reasonable to assume that anything it consumes is gone forever, dropped into the void, erased from the story, a final period at the end of a sentence no longer readable. But physics is rarely so willing to discard its data. The laws that govern the universe, from the fluttering rules of quantum mechanics to the smooth curves of classical motion, have a preference for preservation. In quantum theory especially, information must always be conserved. You can scatter it, you can bury it in complexity, but you cannot delete it. Every wave function, every interaction is like a cosmic ledger, ticking forward, but never blanking out a line. So what happens when you throw information, say, the atoms of a book, the spin states of an electron, the memory of a falling astronaut, into a black hole? Stephen Hawking faced this dilemma in the 1970s. He showed, surprisingly, that black holes are not entirely black. Through the subtle effects of quantum field theory near the event horizon, black holes emit a faint thermal glow, now called Hawking radiation. Over time, they radiate energy, and eventually this means they evaporate. But this quiet leaking of energy creates a puzzle. If the black hole disappears, and all we're left with is a spray of featureless radiation, then the information that fell in is seemingly lost, gone, not scrambled, not hidden, just erased. This contradicts everything we thought we understood about quantum mechanics. It's called the black hole information paradox, and it's still one of the deepest, unresolved questions in physics. The radiation that escapes is thermal, that is, it carries no fingerprints. It does not preserve the complexity of what fell in. It does not remember the shape of a photograph, the texture of a thought, the motion of a collapsing star. And so, the question becomes, is this radiation just noise, or does it somehow, somewhere, encode the story of what was lost? Over the years, many ideas have been proposed. Some suggest that information is somehow imprinted on the event horizon itself, encoded in a fine-grained pattern like ink pressed into invisible parchment. This leads to the notion of black holes as holograms, objects whose surface area, not volume, contains their informational content. It's a strange idea. It means that perhaps every object that falls into a black hole leaves a trace, not in the depth, but on the skin, the boundary, a lightless mirror that remembers what it reflects. Others argue that information escapes in subtle patterns within the Hawking radiation, that while the radiation seems random at first, its underlying structure may carry the blueprint of what fell in. Like ashes from a fire that, if rearranged just so, could reconstruct the burned pages. Still others believe that the paradox reveals a gap in our understanding, that neither relativity nor quantum mechanics is quite enough on their own, that only a complete theory of quantum gravity, something like string theory or loop quantum gravity or some future insight yet unnamed, can resolve the puzzle. Whatever the answer, the question itself has transformed our view of black holes. They are no longer just celestial drains. They are storied objects, woven into the deepest conversations about information, entropy, and the structure of reality. And this idea, that even the darkest places might remember, has poetic weight. It means that nothing is truly erased. Not your thoughts, not your actions, not the starlight that wandered too close. It might fall in, it might be hidden. But the story, in some form, continues, whether in the surface of a horizon, in the entanglement of evaporated photons, or in the soft math of a theory not yet written. Perhaps black holes are not the universe's erasers, but its archives. Libraries sealed, not burned, still holding everything they've taken, waiting to return it in a language we don't yet speak. And if that's true, then even a black hole becomes an act of translation, not destruction. A process through which information passes from one form to another, unreadable for now, but not lost. Tonight, as you drift towards sleep, imagine a single particle of Hawking radiation, quiet, faint, ancient, emitted from a black hole 1 billion light years away. It flies outward, carrying not just energy, but a riddle, a whisper of something once bright, now hidden. And though you may never catch it, though you may never read its message, you are part of the same story. The same laws of conservation that protect the information in black holes govern the atoms in your hands, the warmth in your skin, the glow of thought as it gently flickers behind closed eyes. And so, rest easy. The universe does not forget. Even in its darkest corners, it keeps the light somewhere, if not to be seen, then at least to be known. Close your eyes, just for a moment. Imagine you're standing outside, far from cities, under a night sky so clear that stars seem to whisper from every corner of the heavens. Some of the light reaching your eyes left its source hundreds, thousands, even millions of years ago, long before you were born, before your parents were born, before stories had names or years to rest in. You are not just looking at stars, you're looking into the past. This is one of the quietest truths in all of astronomy. When we gaze into space, we gaze backward in time. The farther away something is, the longer its light has taken to reach us. Every star is a timestamp. Every galaxy is a delayed message. A photograph sent without asking for reply, drifting through darkness, arriving precisely when the universe allows. And there is one kind of light, older than all the rest. It's not the glimmer of a nearby star or the soft glow of a distant spiral galaxy. It's not even light from the first suns to ignite. It is older than planets, older than atoms in their current form. It is the cosmic microwave background, a faint glow that surrounds us in every direction. It is not visible to your eyes, but it is there, always, quietly filling the universe with a whisper that began nearly 14 billion years ago. This light comes from a time when the universe was young and hot and dense, a chaotic fog of particles too turbulent to let photons travel far. But eventually that fog thinned, atoms formed, and suddenly light could move freely. It escaped, and it's been travelling ever since, not just through space, but through everything that ever happened, past galaxies forming and dying, past stars flickering to life and then fading, past all the stories, all the collisions, all the silences. It has never stopped. Today that ancient light is cold, just a few degrees above absolute zero, but it's still here, still reaching us, still reminding us that the universe once began, and it still remembers the moment. And now we return to you, because the atoms in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, were not born here. They were made in stars, forged in their cores under crushing pressure and unimaginable heat. Those stars lived, aged, exploded. They scattered themselves across galaxies, and over time, that stardust formed planets, water, trees, you. So when you think about the light from distant galaxies, from stars long dead, you're not just observing history, you're connected to it. You're a product of it. Not metaphorically, not poetically, literally. Your body is made of ancient remnants, organized into thought and movement, into curiosity and presence. You're made of time, not as a victim of its passage, but as a testament to its unfolding. And just as you're made of atoms formed in stars, you're also surrounded by the light those stars released. When you look up, you're seeing not only what was, but a reflection of what became you. The sky is not distant. It is a mirror, and it remembers. So much of what we think of as now is actually delayed. Every light you see from a star is old. Every galaxy in a photograph is already changed. Even the sun takes over 8 minutes to reach us. You never see anything in the present. You see the past arriving. And somehow, that makes it more beautiful. It means that every moment is a mosaic of what once was. It means that what you do now will echo forward. Light that leaves Earth tonight may, in thousands of years, reach someone else, somewhere else, if they exist and know how to see. You will become part of the story. There is no moment untouched by light, no memory so quiet that the universe cannot record it in some shimmer somewhere. Even the darkness between stars is filled with old photons stretching as the universe expands, fading but never quite gone. So as you lie still tonight, know this. You are not only in the universe, you are of it. Your breath carries elements formed in stellar cores. Your thoughts are woven from atoms that were once the hearts of dying stars. The light that touches your skin is older than cities, older than words, and somewhere, far away, photons that touched you, your cheek, your eyelashes, the skin of your hand, are now moving outward, endlessly. They carry no intention, but they carry you, not your thoughts, not your choices, just your shadow, your warmth, the trace of your presence. They will go on, perhaps forever. Light does not age, it simply travels, and because of that, some part of you is now a traveller too. There is something uniquely strange about a photon, the smallest unit of light. It has no rest mass. It cannot be still. It cannot slow down. It travels at the speed of light because that's the only way it can exist. And because it moves so quickly, time does not pass for it. Let that rest for a moment. From your perspective, light might take billions of years to cross the universe. It might leave a distant galaxy when the Earth was still molten, travel through the expanding void, and only now reach your telescope or your eyes. But from the photon's own frame of reference, if such a thing can even be said to exist, it simply departed, and then it arrived, instantly, without aging, without waiting. It never experienced the journey. It was always already here. This is not science fiction. This is what Einstein's equations predict. When an object travels at the speed of light, the time between departure and arrival becomes zero from its own perspective. The photon does not have a story that unfolds in the time. It is the story, a connection between events, a thread stretched tight across a cosmic distance, but never itself slack, never burdened by the minutes it crossed. And yet, that same photon carries with it the evidence of time. It reflects the movement of stars, the warmth of planets, the transformation of galaxies. It tells you what something looked like long ago. It allows you to build history out of light. It is timeless. And yet, it is the only reason you can perceive time at all. You're not like a photon. You have mass. And that means time flows through you. You feel it, slowly, softly, sometimes painfully. You age. You change. You remember. You hope. You carry the weight of moments stacked like folded pages inside your mind. But light does not carry. It simply moves. Still, you are not separate. The same universe that built photons built you. The same math that governs their motion governs yours. The difference is not opposition, it is relationship. If light is the rhythm, then you are the dance. If light is the song, then you are the echo that gives it depth. And in a sense, time itself moves through you because you slow it down. Without mass, without resistance, without awareness, time would be meaningless. A photon cannot remember, it cannot wait. But you create the narrative. When you speak of before and after, you are describing what light cannot experience. You are the witness, the translator, the slow flame in a fast universe. It's easy to imagine that light is faster, therefore greater. But that's not quite right. Light is constant, predictable, beautiful in its simplicity. But you are complexity, you are hesitation, you are possibility. Light never wonders, but you do. You imagine, you pause. You feel the difference between yesterday and tomorrow. You hold hands with memory. You lie awake and ask questions that photons will never know. And yet those same photons illuminate your thoughts. They carry information to your eyes, to your skin, to your cells. They bring warmth, vision, growth. They allow you to see a candle in the dark, a sunrise over water, the shimmer of leaves in the breeze. Without light, there would be no colour, no contrast, no shadow, no signal from the past. Without you, there would be no meaning in any of it. So sleep now, little flame of complexity. Let the photons pass. Let them go on their journey without you. You don't have to be as fast. You don't have to reach across galaxies. You don't have to arrive instantly. Your power lies in being slow enough to feel, slow enough to wonder, slow enough to love. Time may move through you, but it does not rush. It folds itself around you like a blanket, warm and weightless, shaped by your presence. Your heartbeat does not match the speed of light. It matches the tempo of life, and that's more than fast enough. So tonight, as you rest, think of light not as a ruler, but as a reminder. It doesn't pause, but you can. Let the photons race. Let them trace their perfect lines across the void. You have your own pace, your own curve through time. You're not behind, you're not lost. You're exactly where you need to be, glowing quietly in the rhythm of a universe that made both speed and stillness. If you've ever watched children running freely across a field, or water rushing over smooth stones, you may have felt the beauty of motion without boundaries. The idea that something could go forever, could move without edge or edge case, has a kind of dreamlike charm. But even dreams, when they linger long enough, begin to take on structure, a pulse, a pace, a frame. In physics, that structure is written, again and again, into the number 299,792,458. That is the speed of light in a vacuum, nearly 300,000 kilometers per second. A value so specific, so immutable, that it defines not only how fast things can move, but how reality is allowed to unfold. We sometimes call it a limit, as if it were a wall. But it's not a wall that was imposed from the outside. It is a property of space and time themselves. It's not that nothing wants to go faster, it's that faster becomes meaningless. The equations don't allow it, not because they are prohibitive, but because without the limit the story breaks down. To see why, we have to look not just at speed, but at consequence. Without a maximum speed, there would be no sequence of events that all observers could agree on. A cause could follow its effect. A message could arrive before it was sent. Reality would lose its shape. Memory would untether from meaning. Communication would dissolve into contradiction. Imagine trying to write a sentence if letters could appear in any order, with no rules to guide which one comes next. There would be no words, no grammar, no comprehension, just static. The speed of light prevents that static. It doesn't just govern how fast light moves, it defines causality. It draws the line between before and after, between here and elsewhere. It gives shape to the web of interactions that make reality navigable. Even the space between you and this sentence, between your eyes and the screen, is filled with light moving across it. That light doesn't just reach you. It tells you that something is there. It tells you when it happened. Without that, the world would be like a movie with no frame rate. Blurry, incoherent, and impossible to follow. The universe's speed limit is what allows story to exist. And you are a story. A sequence of moments, each leading gently into the next. You do not experience everything all at once. You wake, you walk, you remember, you forget, you speak, you pause. Every step you take through time is possible because events unfold at finite speed, because light does not instantly bridge all gaps, because the universe waits for itself, and even that waiting has limits. There is a cosmic horizon, the farthest distance from which light could have reached us since the Big Bang. Anything beyond that is not only invisible but unreachable in principle. Not because we lack the tools, but because the tools themselves are constrained by the structure of space-time. The light hasn't had enough time to get here, and so those regions of the universe are not part of your visible story. Not yet. We live in a universe that expands, and as it does, distances stretch. Some galaxies are now moving away from us faster than light. Not because they are breaking the speed limit, but because space itself is expanding between us and them. The speed limit still holds locally, but the very fabric of reality is stretching the map beneath our feet. And yet, even in this vastness, the speed of light continues to serve not as a barrier, but as a rhythm, a metronome, a gentle pulse that defines what we can see, what we can know, and when we can know it. Think of it like the speed of sound in air. You don't hear thunder the instant you see lightning. The flash reaches your eyes at light speed. The sound follows more slowly. You count the seconds, you measure the gap, and in that gap, you find distance, you find shape. The delay is not an error, it's information. It tells you where you are, where the storm is, and what connects the two. Light gives you that same gift on a cosmic scale. The delay between emission and arrival becomes a map of time itself. And so, when we ask why the universe has a speed limit, we're really asking, why must reality unfold gradually? The answer may be, because without that gradualness, nothing would make sense. There would be no identity, no motion, no thought, no conversation. Everything would collapse into simultaneity, and in simultaneity, nothing can change. A speed limit doesn't constrain change, it enables it. It allows stars to form, light to travel, neurons to fire, music to be played, and lives to be lived. It gives the universe its beat. Not because something decided it should be that way, but because this is the only way that way can exist at all. And so, as you lie still tonight, know that even the stillness is paced. The silence has tempo. You are part of a world where not everything happens at once, and because of that, things happen in beautiful succession, like notes, like footsteps, like heartbeats. The speed of light is not a prison, it is a page, and time is the story written across it. By now, you've traced the path of light, from the birth of the cosmos to the silent edges of black holes. You've watched it bend in gravity's embrace, slow the ticking of time, cross the emptiness between stars, and return as faint echoes from a past that still touches you. But before we end this journey, there's something to remember, not about the light itself, but about you. For all the equations and paradoxes, all the bending and stretching of space-time, light remains untouched by time. It doesn't wait. It doesn't remember. It doesn't arrive or depart. A photon knows no before or after. It simply is. A spark without a clock. An existence without pause. And yet, within you, a piece of that same light burns. Not because you move fast. You don't. You walk. You stop. You rest. You age. You carry memory like a candle carries scent. Fragile but persistent, shaped by the air it moves through. You live within time's current, feeling every ripple. That difference, the one that slows you down, is what makes you beautiful. You don't escape time. You give it meaning. You stretch moments between heartbeat and thought, between memory and hope. You gather warmth from passing hours, turn them into stories, songs, and quiet laughter. A photon can cross galaxies, but it cannot do that. It cannot feel wonder at the distance it has traveled. It cannot miss what it once illuminated. You can. Time bends gently around you because you have mass, a quiet weight that presses into the fabric of the cosmos. Even now, as you lie still, gravity folds beneath you, and time moves softly along its curved path. If you were pure light, you would never feel that. No dreams, no echoes, no before or after. But you are not light. You are lit. The glow you carry, in thought and kindness and curiosity, is not measured in speed. It's something slower and infinitely richer. Awareness, presence, the ability to look, to care, to remember. Light rushes forward without noticing where it's been. But you, slow, breathing, fragile, are the only one who knows you are moving through time at all. That knowing makes you more than an observer. It makes you part of the story. You don't just pass through the universe, you leave traces in it. A photon forgets, but you remember. You hold moments long enough to turn them into meaning. You take light and make it human. Memory, emotion, reflection. And tonight, you followed that same light to this quiet edge, a place where the universe still glows, not because you're chasing it, but because you've paused long enough to see it shine. You don't have to keep up. You don't have to understand everything. The universe has never asked for speed, only for stillness, for wonder, for the patience to exist slowly in rhythm with the stars. You are not apart from light, you are its echo, shaped by time, cooled by gravity, warmed by suns. You are resting now in the same darkness that carried the first photons from the birth of everything to this moment on your skin. And as you drift into sleep, remember, the universe continues, quietly, endlessly, like breath. You are part of that rhythm. You are not late. You are not behind. You are not lost. You are resting in the pattern that made you. And somewhere, far away, light still travels, carrying in its endless motion the faint and beautiful memory of you.